Next talk is by Jie Shan at Cornell. She's going to tell us about strong correlations in 2D semiconductor Moire superlattices.
Thank you, Eun-Ah, and the other organizers for giving me this opportunity to share our recent experimental results on the correlated states in transition metal dichalcogenide Moire systems. First of all, I would like to thank my team at Cornell, a group of highly talented and devoted students and postdocs, Yan-Hao Tian, Li Zhongli, Ting-Xin Li, Yang Shi, Chen Haojing, who's joining UCSB as a new faculty member, Zui Tao, and Professor King-Fan Mak, who co-supervised the group with me. And of course, this work wouldn't have been possible without high quality bulk crystals, tungsten selenide, tungsten sulfide, grown by the Columbia team, and also boron nitride crystals from National Institute of Material Science in Japan. The theoretical support was provided by Allan McDonald from UT Austin, Veit Elsa, colleague at Cornell, Liang Fu at MIT. We also benefited from discussions with other theory colleagues at Cornell and elsewhere, including Eun-Ah and her group. So we invite you for comments and suggestions. Okay. Okay. So Moire superlattices for 2D van Waals materials have become a new platform to study electronic correlations by introducing new energy and the length scale. For interacting quantum particles on the lattice of period A, the ratio of interaction energy to the bandwidth or the kinetic energy increases linearly with the particle mass and also the lattice constant A. For transition metal dichalcogenides, the particle mass is on the order of half electron mass, and the dielectric constant is on the order of 4. Then for a typical Moire lattice period of 10 nanometer, this ratio is around 5. But when you have a strong Moire potential, and this will have flat band and significantly enhance this factor. So our work on TMD Moire system is inspired by the discovery made by Pavlo and his team, made in twisted bilayer graphene near the magic angle, where superconductivity and the insulating states were discovered. Pavlo has already given an excellent introduction, so I will skip all that. Let me just say a few words about TMDs, and then I'll move on to the correlation effect. So this is a group of layered compounds consisting of transition metal, moly or tungsten, and the chalcogenides in this prismatic structure in the H polytype. So looking down from the top, it forms a honeycomb, just like a graphene, but with A and a B sublattice symmetry broken. It has been shown by us and the colleagues a while back that in the limit of a monolayer, this class of material is a direct bandgap semiconductor with bandgap occurring at the lowest gap at K and the K prime point of the Brillouin zone. So this separation is on the order of 2 eV. The electron hole mass is on the order of half electron mass, as I mentioned before, and the conduction bands are spin split by on the order of 10 millieV, and the valence band on the order of 100 millieV by very strong spin orbital interaction. And also a spin and the Valley degree is locked in this case to obey a time reversal symmetry. Monolayer TMDs interact very strongly with light, and the optical response is dominated by the strong peaks, exciton peaks. You will see a little bit later, so this gives optics as a very sensitive probe of the system. There are also very interesting optical selection rules that couples light, circular polarized light of opposite handedness exclusively to spin valley degree of freedom. And if you look at the difference between left and the right circular polarized light absorption, you get a probe of the net magnetization in the system. And this you're also going to see a little bit later can be used to probe the magnetic properties of the system. So when you overlay two different TMD monolayers, in this case is tungsten selenide and the tungsten sulfide, they form vertical type 2 band alignment. So if you sweep the Fermi level, the hole will dope into tungsten selenide mostly, and then electron will dope into tungsten sulfide. So if the twisting angle is small between the two materials, so in the case of 0 degree, for example, because there is a large lattice mismatch between the two crystals, about 4%, you're going to get a lattice Moire period of 8 nanometer. And the Moire period is not very sensitive to the twisting angle because of a large lattice mismatch. So this gives us kind of a wider, if you would call a magic angle. So there is no magic angle. You can see the correlated effects, pretty much in a very large range of, compared to graphene, of course, twist angle. And also this significantly reduced twist angle disorder. And this Moire period introduced the Berg refraction for electrons and leads to mini brilliance on this mini Moire bands. So I'm only showing the lowest energy conduction and highest energy valence bands here. Okay. It has been shown by Allan McDonald and his student Shanfeng Wu a while ago that the system can be described by a single band Hubble model with two parameters: the on-site Coulomb repulsion, which was estimated on the order of 10 to 100 millieV, and also inter-site hopping, which is on the order of 1 to 10 millieV. And this hopping parameter decreases exponentially with decreasing the twist angle. Okay, so let's just briefly compare the twisted bilayer graphene moire and the TMD hetero-bilayer moire. Because the bands are topologically trivial, so localized linear orbitals can be constructed in this system. The Moire potential is also stronger, so you generally see more robust correlation effects. And we also have a smaller number of degeneracy. We only have spin valley degree of freedom. It's a twofold degeneracy. And as I mentioned before, the twist angle range is pretty wide to observe strong correlation. To make samples devices, we use pretty much the same technique as twist angle bilayer graphene. So we exfoliate monolayers on silicon substrates, and then pick them up, stack them. And we can, using nonlinear optics to determine the crystal axis of those monolayers and then stack them with a very well-defined twist angle. And here is just an example of the device, So the Moire superlattice is embedded in hexagonal boron nitride, and then we can add top and the back gates. And you can also put a contacts on the Moire system. So the top and the back gates allow us to independently tune the doping density in the Moire superlattice and also electric field perpendicular to it. So in this study, I will only discuss the doping effect because for the hetero-bilayer, there's a pretty large built-in electric field. So the electric field effect is negligible. So in terms of the measurement, we can send the light through the whole structure, look at the reflection, and this can be done with slightly smaller than 1 micron spatial resolution. We can look at in-plane or out-plane transport, and we can also measure capacitance, like what Pablo described, the compressibility measurement, but not a local, but global for the whole thing. Okay, so let me present the results on half filling of the Moire band, or the filling factor equals to 1 for the Moire superlattice. So 1 particle per lattice. So this is the temperature dependence of the in-plane resistance of WS2 and WSE2 Moire superlattice at 1.5, well, from 5 to 150 Kelvin. First, let's ignore the large resistance near 0 filling factor, and this comes from the non-ohmic contact resistance because of low density and a large band gap semiconductor. We still have challenges there. You see 2 pronounced peaks, one at the filling factor 2 and the other one at the filling factor 1. And then they disappear, when you warm up to a certain temperature. So the insulating behavior at the filling factor 2 is pretty well understood from single particle picture. It's a band insulator. And the insulating state at the filling factor 1 requires a strong correlation. So when the Coulomb repulsion is large enough, it costs more energy to put a charge on two charge on a single site. So you have a Coulomb gap on the order of U opens up, and this is just a kind of a typical Mott insulating state picture. We can estimate the parameters a little bit from this measurement. So the half filling of the band, or the 1 particle per site peak, mu equals 1 peak, vanishes at temperature around 150 to 200 Kelvin. That gives us a lower bound of the on-site Coulomb repulsion to be about 20 millieV. So the ground and the low energy excited states of the Mott states are determined by interactions between the localized magnetic moments that survive charge localization. So to gain insight into the magnetic interactions, we measure the magnetic susceptibility as a function of temperature and perform Curie-wise analysis. And that's pretty much, do the measurement of susceptibility at a high temperature and try to extrapolate to get the nature of interaction at low temperature. So if the susceptibility diverges at 0, that's paramagnetic. And if it diverges at a positive temperature, low temperature, that's ferromagnetism. And if it's at negative wise temperature, it's antiferromagnetism. And experimentally, it's more convenient to do this, as 1 over chi and do linear fit. And this is the result. We use a difference between left and right circular polarized light and other magnetic fields, and then look at the slope. So this is the chi we measured as a function of temperature, and 1 over chi fit. So we got wise temperature on the order of -1 Kelvin. And in the picture of super exchange for Mott state, this temperature gives the magnetic coupling constant J, which is T squared over U. And we already know that U is on the order of 20 millieV, and J is 1 Kelvin. That gives T to be on the order of 1 millieV. And this value is in good agreement with some DFT calculations. And this also gives us a ratio of U over T on the order of 20, and that's in the strongly correlated limit. So it's consistent with the Mott state interpretation. Okay, so we've already seen that the in-plane electrical transport can give you a signal of the Mott state. And interestingly, we can also observe this state using optics. So what I'm showing in the top panel is the peak of the exciton absorbance as function of filling. And then you can see, the two bumps here. One corresponds to a band insulator, and the other one corresponds to the Mott state. But if you have a good imagination or sharp eye, if you look at the counterpart more carefully, you see, okay, it looks like here and here, you also have kind of an enhancement of the exciton absorption. And this probably also tells you that your sample is in some kind of an insulating state because the electron-hole interaction is strong at those fillings. And Fernandes' group at Berkeley invented this pretty clever scheme to measure the charging dynamics into the Moire superlattice by optically looking at the connected piece of monolayer, see how the exciton change when you dope the superlattice. And they were able to see, the 1/3 and 2/3 peak in their resistance channel. So, and they assigned this to generalize the Wigner crystal state of holes in the TMD Moire superlattice. So holes try to avoid not only double occupancy in one site, but also simultaneously occupancy of adjacent states. So they like to be away from each other as much as possible. So insulating states at the fractional fillings have not been observed in graphene Moire system. So the emergence of these Wigner crystal states suggests that even the intersite, the long-range Coulomb interaction is larger than the Moire miniband bandwidth. When the gauge separation, so in our devices, typically they are like 40, 20 nanometer away from the sample. It's bigger than the Moire period. The intersite Coulomb interaction is not very well screened. So it's the simple Hubble model with only on-site repulsive interactions is not adequate to describe the system. We have to include the long-range Coulomb interactions. But if we only consider the fractional filling, double occupancy is unlikely. So in that case, you can make U go to infinity and drop this term. Okay, so next I would like to switch gear and talk a little bit more about what's happening at the filling factor less than 1. So recently, we developed a new, we call it exciton sensing technique to study the behavior system for fractional fillings. So the idea is following. I told you that exciton response from monolayer semiconductor is very strong. So the electron hole, they form like 2D hydrogen atom-like object. they form a series of Berg states. So the fundamental state is this 1s, has a ball radius about 1 nanometer. The 2s state has ball radius of 5 nanometer, and 3s, they'll be bigger. So the bottom line is that, for those excited exciton states, the ball radius is much bigger than the thickness of the sample. So the field lines are outside the material a lot, and it's very sensitive to whatever is nearby. So the exciton binding energy in the simple picture scales as the dielectric constant of the surrounding to the -2 power. And the oscillator strength will also scale with the dielectric function of the surrounding medium. So if we put our Moire system sort of next to it, then if it's metallic or compressible, then we should see a smaller binding energy and a lower oscillator strength for the, for example, 2s exciton. And if the superlattice is insulating, we should see larger binding energy or higher intensity for the exciton. This is the realization of the scheme. So we put a monolayer of tungsten selenide, the exciton in this material as sensor, about a nanometer away from the Moire superlattice. So the spacer kills any direct electronic coupling between sensor and the sample, but still, relatively small compared to the ball radius. So you get a sensitivity. And we chose this material such that the optical response of different layers, sample and a sensor, is separate into different energies, so you can separate them. So let me show you the optical spectrum of the 2s exciton in the sensor as function of gate voltage, which is doping. Okay. So when you apply positive gate, you dope electron into the system. So we are doping WS2 layer. And then if you apply a negative gate voltage, you dope holes into the WSE2 layer. Okay. And the y-axis is the 2s exciton energy. Okay. And the blue means higher absorption, and the red or orange means low absorption. Okay. So the highest 2s exciton energy is at nu equals 0 when sample is charge neutral, and this is of course because that's the largest band gap insulating state of this material. And the next is the one at nu equals to 1, the Mott state, and we also see at the band insulator state right here. And then you see peak at 1/3 and 2/3. Those are the generalized crystal states discovered earlier. And then we see a bunch of others, so total on the order of like 2 dozens of those insulating states. So we just calibrate the density and the filling factor, and here are the corresponding filling factors. And then experimentally, we can do the same measurements at different temperature and to map out the ordering temperature for those states. So I put them in this plot here. The Mott states disappears at a temperature above 150. That's consistent with our electrical transport measurements. The electron side and the hole side display almost identical correlated insulating states with similar energy scales, suggesting that the same correlation effect is in play. But the states generally have higher TC on the electron side, and the more states are visible. And then for each site, the states above filling factor 1 are generally weaker than the states below filling factor 1. And also, there is some kind of a symmetry about filling factor half for all the fractional states. And this is understandable if you just think of the classical picture of occupied states and occupied spots and the empty spots to be symmetric. So 1/3 and 2/3 is a pair, and 1/4 and 3/4 are another pair, for example. So in the limit of
Jie,
yeah.
You have a little less than 5 minutes left.
Okay, good. Yeah. Okay. So in the limit of negligible bandwidth, all those insulating states, the fractional fillings are Wigner crystals that are described by, for example, the configurations showing here, with increasing the parameter T. Quantum fluctuations can induce charge leakage into the empty sites and turn Wigner crystals into some kind of a charge density wave with reduced spatial modulation in density. And then if you increase T even more, then of course you're going to melt those. I'm not going to get into the detail of this now. If there are questions, I'll get back to this. I just want to point out kind of another feature, the filling factors between those insulating states. We seem to see some kind of compressible states. Okay, so let me just say quickly about the quantum effects. So we expect in the classical picture that everything to be symmetric about filling factor half, but we don't. The lower fillings are stronger, and that's because they have lower density, and also those guys are weaker, and I think this is all related to quantum effects, and also the electron hole, the difference between the two probably also tells us about the difference in bandwidth of conduction band and the valence band. So in my remaining few minutes, I just want to point out kind of an interesting feature of a few of those states. For example, at half or 2/5, 3/5, they break a rotation symmetry. So those states electronic strike phases. So we try to detect this experimentally using optical technique. So if the sample has anisotropy, for example, has a fast and slow axis, larger optical conductivity, smaller optical conductivity along different directions, we put the sample between a pair of across the polarizer, and the polarization of light will be rotated, if there is optical anisotropy, and the rotational polarization will be translated into change of leaked light intensity from the analyzer. And then we can also determine the anisotropy axis A and B by looking at the dependence of the angle of the sample. So indeed, we've seen anisotropy relatively strong, peaked at filling factor half, and anisotropy actually occurs between 1/3 and 2/3. And the peak at half decreases linearly with temperature and disappears around 35 Kelvin. And as I said before, anisotropy also at the filling factors between those insulating states and suggests some kind of a pneumatic schematic phases. So because we have a good, sensitivity at half filling, and we try to do this more carefully, as I said, we can determine the anisotropy axis by rotating the sample, and it follows very nice sine function. And then from, where the peak occurs, you can determine the orientation of the anisotropy axis. So it's summarized in this contour plot. So this is our sample, and the scale bar is 2 microns. The color tells you about the anisotropy angle, so it's 0.5 degrees, that's the maximum. So yellow means high anisotropy, blue means low or negligible anisotropy. And the bars, the lines here, direction shows the direction of the fast axis, and the length shows you the size of theta 0. It's the same as color. So it looks like there are domains, you have fast axis oriented pretty much along every possible angle. And we did a histogram of this result. And you can see that there are 2 pronounced peaks, around those 2 angles. And we've also been able to measure the superlattice crystal orientation. So 30 degree, 60 degree, they correspond to the zigzag and armchair, direction of the superlattice. So those 2 peaks actually correspond to those pictures I'm showing. So this is our proposed stripe orientation, linear or zigzag chain for those 2 peaks. How much time do I have left?
I think you have about -1 minute, or maybe.
Oh,
maybe
okay, okay. Okay, so I should finish here. I'm going to skip this, and I'm going to put up my summary. So I'm not going to say what we did. I think, the system is very rich, and research is only at early stage. So the big question is whether there is superconductivity in the system, and whether the superconductivity is unconventional. Is there effect of topology, so interplay of topology and correlation? And because we are, sorry for the typo, so we are playing with electron holes. So the question is, whether you can realize both Hubble model in this system. But then, of course, there are many challenges for experimentalists. I just put up a couple here. I will stop here and be happy to take questions.
Okay, thank you. That was a wonderful talk. So there are a couple of questions. Now, everybody, please raise your blue hands if you have questions. First person to raise the hand was Oscar. So, and after Oscar, next person is Rafael wanted to ask a question. So we'll go Oscar and then Rafael. Oscar, please. You can unmute yourself,
Yeah.
Oscar.
So thank you very much for the beautiful talk. Is there any technical reason which would prevent using this amazing exciton sensing technique on twisted bilayer graphene?
Oh, okay. I don't think there is fundamental difficulties. So you can look up. We have a archive paper, just testing this technique on graphene and graphene on hexagonal boron nitride. We haven't done the real experiments, for twisted bilayer graphene yet. That can be done. I think we've been mainly concerned about how to get twist the angle, magic twist the angle reliably every time. So
thank you very much.
Yeah, I think it can be done.
Next question, Rafael, and then after that is Efrat.
Hi.
Rafael, yes.
Yeah, very nice talk. I was wondering, when you looked at nu equals 1 filling, is the temperature dependence of the resistivity? I assume it's some activated behavior, right?
Mm-hmm.
I was wondering what is the gap there, and if you guys know how it is affected by magnetic field.
Oh, okay. Yeah, so so this is just the in-plane transport, as you said, so we have not pursued this route, but we have done compressibility measurements. It pretty much, it gives you a more accurate idea of the gap size. And it changes with magnetic field, and you can extract the G factor out, yeah.
So, but what kind of values you get for this gap, and does it go up or down? I'm just trying to compare with what is known for twisted bilayer graphene.
So the
just like orders of magnitude in this.
Yeah. So the change is pretty small. Let me try to. Okay, so it increases a little bit with magnetic field, and you get something like a G factor on the order of 10. That's
okay.
Yeah.
Thanks.
Okay, next question is Afra Shimsani. Everybody should please try to keep your questions short so that everybody has a chance to ask. After Efrat will be Erez, and that may be the last question. We'll see. Efrat, please, you can unmute yourself.
Can you hear me now?
Yes.
Yes.
Okay, so the question is whether in these fractional filling Wigner crystals you expect, or do you have any non-trivial spin ordering?
Yeah, so that's a very good question. We are in the middle of studying the magnetic properties of those states, so intuitively you would expect very low magnetic interactions, when the filling factor is very low, right? But at those Wigner crystals, depends on the detailed configuration, so the whether super exchange the most effective magnetic interaction, some other channels may kick in, and some of the for some states super exchange can cancel out, if you take everything into account. So actually this topic is very interesting. So we expect to see interesting effects.
Okay. Next question, Erez.
Hi, Jie. Thanks for the talk. So when you showed these domains of the different orientations of these stripe phases, I think you towards the end. Right there, yeah. So the idea that these two states in the bottom panel F, kind of, you think that they're actually part of, so these are two possibilities that are consistent with the data, or actually you think that part of this system is in these kind of straight stripe states, and another part is in the zigzag states?
Yeah, so we think the linear chain and the zigzag chain probably have comparable energy, those two states.
Even though they're not related by symmetry, so you would think that they're kind of different. In general, you would think it's either one or the other.
I think it depends on the ratio of different V's, the interaction energy. You can get either one to have a lower energy than the other one. So we think that they probably are comparable, those two states. And, we must also have strain in the sample, and that can also change things a little bit.
All right, thanks.
There was one question asked through the chat window from Saurabh Srivastav. Usually it is believed that the 0 degree and 60 degree is different in TMDC heterostructure. Do you expect that near 60 degree, one will get stripe bases? That was a question I just read.
Okay. So 0 degree and 60 degrees are different for the TMD superlattices in terms of some spin alignment, in those bands. We only observed this in 0 degree sample. We haven't been able to see in 60 degree samples yet, but our probe is about 1 micron. So in order for us to see the stripes, the optical electronic anisotropies, it has to, the domain size has to be large enough. So if the domain sizes are very small, then over 1 micron, you're going to average out. So I don't think that there's fundamental reason why, the 60 degree cannot form stripes.
But you haven't seen it?
We haven't, optically.
Optically, okay.
Yeah.
All right. Are there any more questions? If not, I guess, so I have one question. I think we have like 2 minutes, maybe less. The electron hole asymmetry, right? Because they are coming from different materials. The bands are coming from different materials. You don't expect them to be symmetric, right?
Correct.
And perhaps that can also play into the asymmetry around half fillings.
You mean nu equals half?
Yeah. I'm just wondering.
Oh,
because you mentioned that the asymmetry around half fillings, you attribute it to the quantum effects just because you don't see it in classical modeling. But in your classical modeling, you also probably didn't have, electron states and hole states to be different either.
Okay, so this nu equals half corresponds to half filling of the superlattice. It's a quarter filling of the band. So I think, it's more like what I said, that, in a classical case, the empty site and occupied site are fully equivalent. But in this case, the lower filling, certainly has a larger, interaction over kinetic energy ratio. So they are stronger.
I see. All right, I think our time is now up. Let's thank Jie and Pablo again